this is Group 4's presentation, which is me and Chance, and we're presenting on the double star system WDS 09144 plus 5241 SDF 1321AB. So, some facts about our star system. It is located in the northern hemisphere in the constellation Ursa Major. This double star has orbited 975 years, but it has only been observed for 197. Our star is considered a grade 4 physical double. Its grading is from 1 to 9, 1 being the highest sanctity of the star's orbit and 9 being the lowest. So since we're at a 4, that means we're more certain than not to find out our star's orbit. So as you can see in this image, that is where it's located. Our star was discovered by Struve, who was born in Hamburg in Germany. Struve later moved to Russia, which is modern-day Estonia, and became a teacher at Dorpat University, which is likely where he discovered this star system. He was later awarded the Gold Medal of the Royal Astronomical Society for his work. The image on the left is the image that we originally thought was the orbital solution for our star proposed in Teledopy. However, this is an image that I found in Google Images and in fact isn't our star at all. So we thought that the orbit was a very poor fit for the data points, and so the black line drawn through them was where we thought we would have to propose a new orbit. However, the image on the right is taken from Desmos, which is actually the orbit proposed by Chang that is on Teledopy of our star system. This orbital solution proposed by Chang has an R-squared value of 0.996, which is a very good fit for the points, and ours, the orbital solution that we found has a high R-squared value, but not quite as high, with a value of 0.992. We calculated the ephemerity of our star system, which is the expected position angle and separation of these stars, the future position angle separation, and we based this calculation on previous orbital solution data from the 6th orbit catalogue. The actual position of our star varied greatly from what we expected with this calculation. This means that there is probably a deviation in the star system's motion since this orbital solution was published. For our data, we used DSO-14, DSO-17, and AURT telescopes. With our return scanner images, we had a few problems. One of the images returned had extra pixels of light, and another did not contain our star at all. So Chance is now going to show you our plot and data that we did manage to get from other images.
Yep, I'm here to talk about the data and plot by me, Chance Krigler, and Beatrice Miller. So the data was kind of difficult to obtain. We used DSO-17 for our first image, and to do this, you get various exposure times: 40 seconds, 20 seconds, 10 seconds, and 5 seconds. So we ended 40 seconds. So we ended up taking those, and they become very important later on. So you take those and you see which one give you the highest quality image for the lowest exposure time, because you don't want to oversaturate the images. 20 seconds seemed to do the trick. But when we re-requested, we ended up re-requesting on DSO-17, AURT, and DSO-14. Our DSO-17 image, well, it didn't return any images, it instead returned the lovely star field to the left. DSO-14 was saturated, and so what saturation is, in short, is that if you take a scale of how bright the star is, it's not that bright on the edges, going up, and then it goes up and increases as it reaches the middle, and then it hits its high point and then goes back down, right? And then, so how this works is that there is a certain level off of how bright it can be. So that's the maximum number of, that's how many photons it registers. So if the brightness goes above that threshold, it just levels off, and that leads to inaccurate data. and so that's problematic. When we got DSO 14 back, it was saturated as well. In AURT, however, it was not saturated. So we ended up having to use DSO 17 in AURT. But here's why. So of all of the original requested times, all were unsaturated. 20 seconds, as I mentioned before, did the best result. Everything else was saturated, and we were kind of racking our brains as to why. And we found out that it was actually because of the moon. The moon added extra light to the images, so it hit that threshold. So we ended up having to use different images, just varying on how bright the moon was and how that interfered with our measurements. Another thing we did was that we calculated the common proper motion. So, as you can see here on the left, a paper by Richard Harshaw, another statistical tool for evaluating binary stars. If stars have common proper motion, they are likely gravitationally bound. So what common proper motion is that it means that you take the difference of the proper motions of the two stars, as you can see on the graphic to the right, primaries and the secondary, and then you take that difference and you divide it by the secondary's proper motion. And if that number is under a certain threshold, if the scalar is under a certain threshold, then it indicates that these stars are likely gravitationally bound. Our graphs have a very strong curvature, although our star deviates slightly. If you can see here, the patch of the multicolored are the more recent measurements, and that's the over there in the blue is the historical data, and you can see how it deviates from what is expected. Although in total, it still holds a very strong curvature, as you can see here. It does indicate that the star is probably undergoing some kind of change. So, in conclusion, according to the CPM and the Desmos, our star is very likely to be gravitationally bound, and visually it has a very strong indication of curvature. We will likely be able to improve the grade of the star with the publication of our paper. So thank you very much for watching.